Hello and welcome back to Compiler Programming. In this video, I want to try to make as much progress as I can on cleaning up and making sure that our PE32 executable writing is quite robust. So let's dive right in. And I will annotate things that I think need to change eventually and also go through existing fixmes and decide what I want to do first, what I want to do next, and kind of start tackling them one by one. Okay, the first thing here is this should be dynamically sized or correctly estimated. And we can actually do that because we at the point where we start to write out the program, we know quite well what is the size of the data that we have. So this kind of our data segment, and we also already know how to estimate the size of the code. So all in all, we should be able to figure out what is the safe amount of buffer we put here to make sure that everything fits quite nicely. Okay, what do we have next? Next we have this time date stamp, and I think I tried to make it 0, and then the executable loader was quite unhappy. So let's try to do that again and see if that is actually the case. Let's try to run the tests. Okay, so it looks like I was wrong. It's perfectly fine to have 0 here. We can bring in, I think, file analyzer and open up our executable to make sure. I think if we go into p headers, somewhere here there should be, yeah. So basically this is the time date stamp and it is empty. Although it would be nice to know when this file was generated. So let's try to figure out what it is. First, we need to figure out what's supposed to go there, right? We need to know the format. Let's ask MSDN about that. So this is the page for this stuff. Okay. Number of sections, time timestamp. Okay. The low 32 bits of the timestamp of the image, which represents the date and time image was created by linker. Seconds since January 1st, 1970. So it's actually a very weird number to generate because it's not really Unix time and it is not really anything that Windows uses for the time. Let me think for a moment. How would I want to do it? Well, okay. I guess what we're going to do is we're gonna first look up how to get Unix timestamp in Windows and then just multiply that timestamp by 1000, because Unix timestamp is exactly this, except it is in milliseconds. So this is a very strange number, but okay. So let's say C get Unix timestamp and see what we get here. Okay, I don't think we can actually get it like this. So let's ask how to get it in Win32 apps. Okay, so in C++ we can do that, but the question is, can we get it in regular C? So C time, what is that? Okay, that seems to be time.h, AC time.h. Okay, that looks promising. Make time. That looks good, or current time. Okay, get current calendar time. This is timer. Actually, actually does do what we want. So it is number of seconds. I think I saw that Unix timestamp is in milliseconds. Well, I guess I was wrong. Okay. So this is how we deal with this. And I want to get the current time. Should I just timer? Same as time null. Okay. Let's try that out and see if this is something that we can use. So here we do, oops, this. We need to include time.h. Okay, that header at least does exist. And what we want to do now is say time t, current time is time of 0. Okay, that does something, but we are not using current time variable. So what I want to do is to get time since, okay, basically it's just the make time. What does make time return? Returns value of time t that presents local blah blah blah. Is time t just seconds? Okay, time t is an alias of fundamental arithmetic time capable of representing times. Okay, that's good. So I guess I can just take that and put it in here. Let's see what that does. Okay, it's not happy with the fact that we are, those are not the compatible types, but I think we can just truncate it and that would result in what we want. Let's try to run. Okay, that was fine. Let's open this up in File Analyzer and let's see if it shows anything reasonable. Okay, so that's actually exactly what we want. It is indeed 5:43 right now where I am, so that was quite straightforward and easy. I guess I could even just put it like this. Okay, one fix me done. Let's commit that. It commits -m correctly generate timestamp for PE32 executable. Great. Next thing. Okay, so size of code. This is where it becomes quite interesting. As I mentioned, we should be able to figure that out. We already have a function that tells us what it's supposed to be, or at least it tells us upper bound. This means that our executable will actually be bigger than necessary, but in reality, this is perfectly fine, at least for now. So we are going to take this function, and I guess I want to bring it out into here to deal with this stuff, or more precisely into the C file. Okay. Still builds, and now I can use it inside of this code. So let's do that right at the top. I can do U64. Max code size is estimate max code size in bytes of program. Okay, that just gives us the raw number, but we also need to make sure we correctly deal with alignment. And that means that we should extract this file alignment into a variable or into a constant. Maybe we can do this PE32 file alignment. Okay, let's define this here. Define P32 file alignment is 512 bytes. Now we can align our stuff. So we say max code size is align of max code size and P32 file alignment. Okay, this is have a couple of problems. The first problem is we need to take this stuff and allow to define it here. Okay. And the second problem is we have this align function, which I think is in prelude. Yeah. Which actually should be align as 32, but I will not change this for now. I will just add another one that is U64 version of this, and then later maybe do the cleanup of renaming it. Okay, align U64. We can get this stuff, and it works in exactly the same way. It's just that we need to change the types. This is an unfortunate part about C, but you know, you have to deal with it. Align U64, we convert to U64, and the rest actually stays exactly the same. Okay. So now I need to use that version in our code here. Great. So we calculated max code size, and I expect if I print f this and say %x, I should get 0x200 because that is sort of for the only test of writing executable that we have right now, that is the right size. Let's check this out. Okay, something did not work exactly like I wanted because this is supposed to be LLX. Let's check this, and here we go. Great. So we do have 0x200 as the right answer. Cool. So the next topic. We now have code size, so the total size of the buffer will be consisting of several things. Number one, it will be the code size, 2 is data size, and 3 is the size of headers. And the size of headers is more or less fixed. There is going to be a difference in the amount of directories that we plan to use. But besides that, I guess, number of sections, sorry, not directories. So if we define these sections ahead of time, then we should be able to statically know what is the right amount of memory that we need for the headers. Okay, how do we do that? Well, I guess right now we have this image section header array where we iterate and fix up the sizes. What I want to do instead is I want to move this to the top of the function and make it into a fixed array. So let's do that. Basically, now that I'm thinking about it, I could also define a type for the whole header. It will need to be packed so that we can correctly estimate bytes, but it could work. Or I'm not sure what would be the best option. Let's start with this version. Okay, so let's say these are sections. As I mentioned, I will not do it as a pointer. Instead, I will actually put sections here. So this is the, I can take this stuff. And we actually need an empty section at the end, which is also good. Here I will need to add a big fix me to actually write this out. Write out sections. Okay, that sounds good. But this stuff goes now over to here. And at the end, we have 0. So it tells us this stuff, which now can go away. And now we have our data section. So let's take this code and put it over to here. Cool. This is something that we will eventually know, but we only know this after we encode. So one way we can actually do this, if we don't mind a bit of copying of memory around, is to estimate this max code size, then create a temporary buffer for exactly the right size for the code bytes. Then we would know this number, which we need to put in exactly, and we would be able to better estimate the full executable size. I guess copying like a few megabytes of memory at maximum is not too bad, so maybe that's what we'll do. But this comes after we are finishing with this section changes. Okay. This goes out, this goes into here, and we are good. And I guess this is size of data in bytes. This we do know right away, actually. So this is something we can put in. Okay, virtual address, size of raw data. This virtual address basically depends on the size of the full size of headers. So it is a bit of a chicken and egg problem in the sense that we the size of headers depends on the amount of sections that we have here, but then this address in sections is dependent on the size of the headers. But that's fine. Okay, so right now we are putting base of code and size of code into here and then putting them back into sections, but we want to change this around. So this goes now to here. Okay. And this size of code is something that we actually did calculate. I guess we can, for now we can put this number in. It won't be a big problem. So size of code is max code size. Okay. Now, I guess I do want to have the pointers to these sections as separate things. So I would say image section header text section is ampersand sections 1. Okay. So now we can use this stuff. Here we say text section. What is the field? Size of raw data. And the other one is virtual address. Size of raw data. And here we putting virtual address. Address of entry point we will need to calculate, and this is something to do still. The rest seems better. So size of initialized stuff, we can also put this in. So if we say our data section is sections 0, then size of initialized data right now will be our data section size of raw data. So this is fine. Yeah, this is still need to be calculated. That's okay. Size of image is something that we will be able to also figure out. Basically, we will go through all of the sections and just sum up their sizes in sections. Okay. That's fine. Let's try to build this and see what is wrong. Okay. So here, the problem, first of all, this should be called section header, so that all the other code works fine with this stuff. And this means here we need to add header, which is not an issue. Okay, much better. Now the problem is only with the dot instead of stuff. And we do need to write them out. And here we need to say if I is not equals, just thinking if it is easier to keep this stuff here, like this 0, is it easier to keep it here or to write it ourselves? Because the issue is in this loop we assign some fields, but you want the last one to be exactly 0, so that's not great. I guess I can do this and then add a comment. -1 makes sure we do not write anything in 0 termination element. Okay. What's the issue? The issue is that this is a U64, but we actually need to have S32. So that's fine. Actually, let's do this. Max code size S32 is 32 of max code size. And here we do this thing where we do assert fits into S32 of max code size. Okay. Problem is this fits into is not, we don't have it in headers, which is very easy to fix. We actually just need to move it to be over here. Okay. And now we can use it safely. Okay. What is next? Well, next actually is writing out these sections. This stuff, I'm wondering why was it happening after we did everything. So section of set is optional header, size of headers. Okay. Yeah, so we needed to calculate, this is where we calculate the size of the headers, and then we update it inside of the buffer. Since we now prepare it ahead of time, we need to do something better. So what is the size of headers? Let's figure this out. Let's have S32 size of headers. And it might have been a better idea to first try to get this number, check that it matches the previous one, and only then do stuff. But it's fine. Okay, so size of headers is size of sections is size of image DOS header plus size of S32, which is image NT signature, plus size of what? Image file header. So let me copy paste this line. Image file header. And then we have image optional header 64. I'm basically just checking where do we do buffer allocate or buffer append, and this is it. So this seems to be what we want. So let's check how is this working. Now we can take this out and move it up. So size of headers is this stuff, and we don't need to have exe buffer occupied because we have this, and instead of this stuff we just say PE32 file alignment. Okay. I'm not a big fan of this thing, but the rest is actually quite straightforward. Okay. So this moves us to the right offset, which is something that actually does need to happen afterwards. Although because here we are moving to the right section, I don't actually think we need to do this. Instead, we can take this stuff and move it up. So let's put it over to here. And say what? Well, update offsets for sections. Okay, let's see what that does. Size of headers, yeah, that's no longer true. Yeah, that sounds actually very nice. And now we have size of headers here, which we can put in as a number. Okay. And finally, we need to again go through all of the sections. Now with the last one. So we still need that 0 at the end. We don't need this. We don't need this as a comment. We don't need this. We don't need this. Maybe we could say write out sections. And what we want to do is just say buffer allocate exe buffer I guess like so, and the name of the struct is image file header. No, image section header. Yes, it is image section header. Okay, that was quite a big change. Let's see what comes out of that. If that doesn't work out, I will probably just stash this version somewhere and then go a bit slower and step by step verifying. But if it works, well, then it's great. And it actually does work, which is really, really nice. So now we are in a good place because we do know certain sizes ahead of time. There is way less patching, and we fixed a bunch of fixes here. Okay, let's continue on that path. And I actually probably do want to next tackle this stuff. So this we should know, and we can verify this right now. Actually, this stuff is a bit tricky because this is not size of data, it is also size of the all the import stuff. And the question is, can we somehow estimate what that size should be? The answer is probably yes, we could, but it will mean that we would have to copy some of the logic, right? Because we are writing out all of this stuff for imports multiple times in different sizes, and it would be important to not diverge from what we are doing right here. I guess we shouldn't be able to because the format specifies what's supposed to go in there. Okay. Let's first verify that the number that we have at the top actually matches what we have in reality. How would I do that? Well, I guess I can do this, and I can do this. So let's check. Printf, or we can even assert that our data, let's say S32 actual size of our data is this stuff. Actually, it is exe buffer occupied minus this stuff, right? So this is where the section starts, and this is where we are, where the cursor right now is in a buffer. So this would be the size. We probably need to do it like so. And now we can say that assert actual is our data section size of raw data. Actually, is it size of raw data? It is MISC. Let me recheck that. So MSDN image section header. Virtual physical address or virtual size. Let's read this. The total size of section when loaded into memory in bytes. If this value is greater than size of raw data member, the section is filled with zeros. This field is valid only for executables. Okay. So technically, I could overestimate and it should be fine, but let's try to make it match exactly. So misc.virtual size. Let's be more explicit about this. First of all, virtual size. Oops. And virtual size over here. Okay. I'm missing a semicolon. Signed, unsigned, mismatch. Well, let's not convert it then. U64. Okay. Well, let's see how good is our code at the moment, or we are doing something very wrong. And assertion has failed. Interesting. Let's figure out what it is then. Printf %llx and then this. Okay. Okay, this is quite interesting, to say the least. So it tells us that the size of everything that we have output is 22f. Which is quite a lot, and it's more than what we promised it will be, right? So we promised that the size is 14C. I mean, in reality, probably this is not so terrible because we only need part of it in memory, but this seems like quite a bad thing to happen. So let me just recheck that I'm doing it right. And I'm not, because it's the wrong section. It's supposed to be over here. Okay, let's test this. Okay, so this is better. Actually, we only need 6C of space here. And this is something that we can, for now, just hardcode. And after the refactoring, hopefully we can match this. So first of all, now I will do 0x6c, and over here I will change this to this stuff, and let's see if our code still works. Okay, so we do have valid executable if we do this. Let's try to make it break just to see if this actually does anything or it's unimportant. Well, this is kind of unfortunate. So it does seem that no matter what we put into this field, it is working. I guess what the loader is doing is it looking at the size of raw data, and if that size of raw data is more than the virtual size, it just uses this one. And as it says in the documentation, if it's other way around, if the virtual size is larger than the size of raw data, then just fills it with zeros. So yeah, I mean, it's not really important, I guess, what we put over here. Okay, what is next? Next, I guess, let's see if we can write out the our data section without looking at, like, can we do it before we figure out the headers? Is this something that would work? Let's think about this. So what are we doing here? We are using file offset to RVA, but this file offset to RVA is depending on only on the virtual address. And I think we can figure out the virtual address of this section without any problem. So let's first do that. So first of all, let me store whatever we have. Let's recheck the tests are running, and let's continue with the changes. So the idea here now is that we need to figure out these virtual addresses. This is our next step. And these virtual addresses will need to have, it means we need another alignment. And this alignment is PE32 memory alignment. And memory alignment is 1000 in hex. This is just basically a convention and a requirement for executable that as far as file stuff goes, you need to align on at least 512 bytes. I think you can over align, but it has to be divisible by this. And here you need to align on this boundary. So we know size of headers at this point, right? So this means that we should be able to figure out this virtual address for these sections as well. So size of headers, let's rename it to file size of headers. Let's see, it is also used here. And this actually should be P32. Okay, let's call it section alignment, since this is what it's called in the struct. Okay. And now we can say that S32 virtual size of headers is align file size of headers to P32 section alignment. Okay, and this is what we can do. Here we have file section offset and we have virtual section offset. I guess this can go straight into here. Yeah. Okay, so this will update the file one, and we can do the same thing for the virtual one. And if we are successful, everything should still work as it did before. So let's take, it means we are updating virtual address, and we need to append aligned size of raw data of that section. So file size of headers, no, this is going to be this stuff. And this is not file section offset, this is virtual section offset, and this is virtual section offset. Okay. Let's not write it out just yet, maybe, or let's just see if it works. Okay. That does seems to work correctly, which means that we are doing it right. Let's try to mess with it and see it all explode. Yeah, this app can't run on your PC. Good. So this works as expected. And that just means that we can remove this comment and we can put 0 into here. The goal basically is to put 0 in all of these 3 fields and actually in this one as well, and then calculate all of that ourselves. This goes to 0. And let's try it out. Good. So we have less hard-coded numbers, which is great. I think we need to have to put something into here. Okay, size of image. This is something that we can also calculate. So we do S32 size, let's call it virtual for consistency. Virtual size of image is, well, I guess I should create virtual size of headers. Or maybe not. Yeah, no, not really. So we say 0 here. And in here we say virtual size of image is virtual section offset, right? So after we finish this everything, the next offset will be the size that we need to have. And now we can take this virtual size of image and plug this into here, removing this thing. Let's try again. Seems to be working just fine. So what do we have? Well, I guess these ones we can just remove comments because they don't really do anything. Actually, they sort of do and they don't. Let me try to find something like, is there a version here that I can look at? There are obviously a lot of versions. Yeah. What is this? Deprecated, deprecated, deprecated. Great. That looks very promising. And TDDI Win8 and TDDI Win8. So where are you defined? Let's try that again. Interesting. So there is this also Win32 and T stuff. I wonder if it somehow corresponds to this. So let's try to ask the internet or MSDN. How's it called? Major operating system version. P header builder. Let's get docs for C# as well. Maybe they have something interesting. No, they do not. The major version number of required operating system. That's not what I was looking for. Let's try to look here. Operating system versions. Okay, so this is good to know. Getting the system version. Okay. There is version helpers stuff. Can I look at version helpers? Is Windows XP or greater? That's not really what I want, because I just want this stuff. I want to know what I can target. So basically, if we are saying 6, we are saying that I'm targeting Windows Vista. What if I search for Vista in here? What if I search for Vista like this? So this and TDI, they are defined somewhere. I guess I can do like this. This is quite unfortunate, let's just say that. Does this import stuff from somewhere else? I wonder. Win API family. Yeah, I guess there are other places where it is. Okay. STDFX. Not sure how this is supposed to work. Yeah, I guess I'm supposed to define this version ahead of time and then it uses it for comparison, but this is not exactly what I want. This is also not exactly what I want, because this probably will give me this is not what should work here. I guess what I will do is I will just hardcode these values. I'm not interested in anything below Vista, definitely, so I can even do this stuff. So what are the stars? Blah, blah. Okay. So the safe one is 6. Let's just do it that way and say that define PE32 minimum Windows version is 6, and let's comment Windows version. Let's do it like this in Vista. Okay. So that allows us to get rid of this. 0 is actually correct. We want 0. And subsystem version, I expect that this basically is the same as operating system version. Okay, this is going quite nicely. Let's try to get rid of this comment as well. So I'll just search for this stuff. Let's look here. The image compatible with data execution prevention. Well, I guess we are, because it works just fine. What is 32 dep data execution prevention? Let's take a look at these docs and see enable memory protection. When this option enable, prevents buffer overflow. Okay, basically it is going to be enabled by default, so we don't really have to think about it that much. Yeah, okay, good. That's good to know. This is something that we definitely need to allow to specify for user, but this probably will have to do with a separate thing that we need to discuss for compiler, like in general, how do you tell the compiler to target UI versus non-UI applications? And it's only a thing in Windows, but it's still something that you have to do. So it's something to think about. Okay, address of entry point is interesting, and we also need to tackle this. But for now, this is really, really nice progress. Okay, let me look through this. Okay, size of machine code in bytes, that's fine. I guess this we could also put this number and it will be perfectly fine as well. But the next thing I wanted to do was deal with our data and trying to see if we can figure out our data before we figure out the rest of this stuff. Okay, so first thing is we need to understand how much memory we need for this section. And the amount of memory will be a compound of whatever we have in the program itself. So if you look over here, where is it? Yeah, so in here, we don't really put any data into read-only segment. So we only have function main, but we could put something there like we do in other tests. Let me try to find one. Data buffer to show you what I mean. Yeah, so this is more or less where we are using this. I guess this is the only place. So maybe we need to stress that part of the system way more. But the point is, if we have some kind of global constant, so if we want to print out hello world or something like this, we will need to take that into account. For now though, we need to, let's actually deal with this stuff. So address of entry point. Right now, it just points to the start of the code that we have. So we expect that the very first instruction and that we have in our executable is the place where we start executing. And with this setup, it is actually the case. It's all fine. But let's try to do something else and we will see how terribly it will go wrong. So right now, I'm saying that this is the entry point, right? And this is what we are doing. What if instead I did this? And I would say function, whatever, dummy, or my exit, doesn't matter what we put here. Point is, we will take this code and we'll put it here. And here we just say call my exit. We don't really need return here because the entry point doesn't really return anything. It's a void function. So this is actually a better option, I guess. And here we technically also don't need return. It just will add more stuff to our code that we don't need. So let's keep it like that. And let's try to run it. It should be pretty bad. So where are we failing? We are failing in value C, which is not exactly what I would expect, but you know, you never know. In 337, assert byte size. This is very interesting. Let's debug that. And def mass. It's a very large Visual Studio window. Solution Explorer. Let's check that executable is the correct one. It is not. It's supposed to be function spec. And let's start that. Yeah, we are crashing here. What is our call stack? We are calling reserve stack. And we are saying that we need 0 bytes. That's kind of interesting. How can we have 0 bytes? So byte size is indeed 0. But where does it come from? It comes from call function overload. And so descriptor byte size, you're trying to size this descriptor. And this descriptor is null. Okay, that's not good. Where are we? So I guess it's not really happy about this stuff. Let's see. Function value, call overload. Yeah, so it is definitely, don't jump around. Function spec, it is definitely unhappy about this stuff. But the question is why? So descriptor returns descriptor. Oh, I see. So this is actually something that is broken, I guess, at the moment. We do need to have a return value, which is not good. Well, let's fix that. Function C, and the thing is called function overload. Okay. So if return size is more than 8, then we do this. I guess let's do assert instead of this check. So if it is like so, and otherwise we need to say if return size is actually no. So this was correct because we can return bigger things, but we need to check here if return size is not 0, then do this. Because void functions basically don't return anything, so we don't need to do anything about that. Okay, so the tests themselves did succeed, that is good, but if we try to run this, the executable is exploding quite spectacularly. I can probably show what is the issue, or I can just explain it here. Let's try to figure out what our encoder right now is doing with this. Well, it's like, okay, we have this function and we have this function, and we are saying that this is entry point. But actually this is interesting because this should have failed, I guess, or maybe not. Anyway, so we are not actually outputting this function anywhere, because if we look at our code, what we are doing here is we are, let me find this stuff. Yes, so we do function encode of program entry point. And this is not really what we want. In reality, we need to output all of the functions the same way as we do in JIT code. And then we need to point the stuff to the entry point. In the, let's say that is the first instruction that we need to do. We are outputting entry point as the last one. I guess it doesn't really matter in which order we output them. Yeah, it doesn't really matter in which order we output them, but it is important that we output all of them. And right now we are not. So let's look for program end, because it was doing this stuff. And let's see how it does this. Well, if we change this function slightly, so we say program encode functions, and we for now can probably say that it's void. It will get the program and it will get a buffer. Yep. We extract this stuff into here. I guess we don't need this because it's just a very simple loop. Let's not make it more complicated than it needs to be. The point is we do this. Okay, this will be exe buffer. But the tricky part here is that we need to know where does our entry point start, right? Because we are just going through all the functions and we are just encoding them one after another, one after another, one after another. But we need to tell our loader where to begin. So I guess the way we can try to do that is, since in here, where is it? In here, we are saving a particular builder as an entry point. That means that we can probably just compare them and say that if builder is entry point, then we do that. And we need to do that before we encode, because we need to point just before the first instruction, right? So I guess, how do we call this? Well, optional header. How is this field called? Address of entry point. So we put this as 0, right? We're going to be resolving it below. And below, we are saying that address of entry point is a text section virtual address. Actually, let me think about this. We probably can use this helper that we have, file offset to RVA. Yeah, we should be able to do that. File offset to RVA of text section header. Okay. This needs to be like this. And that is nice. Now, let's try to run this and see if it's better than what we had before. And here it comes. So we actually have a working thing. I do want to show you how it looks like in disassembly, because I think it's important to understand exactly how this is working. Tools, debug, step into. So as you can see, previously we would say that address of entry point is just 2000. So basically look at here. But now at the start of it, we have another function. We have that proxy function that we created. I can probably close this one. Sure, save it. So let me try to arrange the windows a bit so you can see better. Basically, this stuff is till here. And we can see that it is indeed the case, because 2a is 42. Then we are moving the address of exit process into arrayx, and we are calling arrayx, and we move out the result, which we technically don't need to, like we are not really using this. So this is an optimization that at some point we will need to do, where if the function doesn't actually care about result, we just don't do anything. But right now we are doing stuff, so that's fine. And this is just restoring stack and then returning. And this thing, these 4 instructions, is what we have here. So this is just a call, and because this call has no arguments, we are fine. We still need to reserve stack space, because that's how the convention is saying that we need to reserve it for the arguments, even if there are no arguments. So that's just something to keep in mind. And I think it might actually be that in here we are doing this wrong, but let's see. Cool. The point is, now we can have multiple functions, and we are not hard coding address of entry point, which makes me very happy. Let me look at this stuff some more. So yeah, we still have a few hard-coded things here, but we can only deal with them if we encode sections separately from the main executable, and it will be quite a big task, so probably something I will handle in the next video. For now, thank you very much for watching. I think we made good progress, and hopefully see you next time.